Welcome to the next installment of gas laws. This time we're going to be talking about van der Waals equation, which takes into account the two big assumptions that we make in the ideal gas law. One big assumption is that particles have no volume. Well, since gas particles are matter, all matter occupies space. Eventually that space is going to become a big deal. And then the second big assumption is that the particles have no forces of attraction between them, which we also know to be false, because if there were no forces of attraction, then gases would never convert to liquids, which is true for ideal gases, but not for real gases. And that's what van der Waals equation gets into real gases. So it gets closer to real gas behavior. So it gets closer to real gas behavior. Let's go to the next one. Wrong direction. Come on. There we go. Oh, jeez, this is taking long enough, huh? All right. Now, the first one we're going to talk about is volume. Well, if we have this whole system, like as the container, and the particles, if we take the actual volume of the particles, take it down to this tiny little bit of space, then overall, that is not significant. But if we lower the top, so we lower the volume, and we have the same amount of gas, so we have that little bit of particles, now that's a pretty significant portion of the available space. Which is to say that our volume is artificially large. That means we need to reduce the volume, and the amount of volume that we reduce it by is the volume of the particles. So we need to remove particle volume. So it's P prime, because we're changing it from the ideal gas law pressure. P prime, same idea, just it's changing what the letter is so that we have different references. nRT stays the same, but then now down at the bottom, we're subtracting from the volume, because that means we need to remove, and the volume that needs to be removed is going to be dependent upon the number of particles that we have, N, number of moles, times some sort of constant. This is an experimentally derived constant, and it's going to be given. Every gas has its own B value, and the unit for B is going to be liters per mole. So that when we multiply by mole, we'll have just liters subtracting from volume. That's our first pressure correction. The other one's a little bit more complicated. So now we're going to get into pressure. So the number two, the second correction we're going to make is pressure. What we need to think about here is the amount of particles that are available for attraction. So the more particles in the area, the more forces of attraction that are going to occur. If we have this one particle going towards the wall, and we have these three particles slightly pulling it back, not a big deal. But if we have this one particle in a whole mess of particles, the more particles we have, the more they're going to be pulling on that particle and reducing the amount of force that it's going to collide with the wall. That means that the pressure is artificially large, because the forces of attraction are trying to bring this particle back towards these other ones, reducing the force moving forward, like reducing the speed. Well, this correction factor, see the P prime from the equation on the other board? The P prime, we need to subtract some sort of correction factor. That correction factor is going to be dependent upon the concentration. Now, we haven't talked about concentration yet, but it's the number of particles per volume. So it's going to be the number of particles in a given volume. It's all about combinations. So the number of particles, we need to relate the number of particles available for making up a pair. So if we have 1, 2, 3, 4 particles, because we're going to keep this simple, we're going to start small. Each of those 4 particles are able to pair up with the other 3. So it's n is 4. That's the number of particles available. Well, we're going to get combinations of n times n minus 1. Obviously, it cannot pair up with itself, but it can pair up with other particles. That's going to be 4 times 3. That means that we have 12 possible combinations. Only here, it's 1 and 2 is counted as 2 and 1. 1 and 2 and 2 and 1 are the same combination of particles. That means that we need to reduce by half. So if we do n times n minus 1 divided by 2, that'll give us 6, counting 1 and 2 as the only combination. And that's what we did up here. Particle 1 with 2, 1 with 3, 1 with 4, 2 and 3, 2 and 4, not counting 2 and 1 because that's already been done. And then 3 and 4. So that's 6. That's 6 possible combinations. That matches this down here. Now, if n is very large, so if n is very large, n minus 1 is going to basically equal n. So if n is 1 million, which is still very insignificant, like that's small, in terms of the number of particles that we will be typically dealing with in a volume of gas. Well, n minus 1 is 999,999. I don't know about you, but if I had to choose between the two, I'd be okay with $999,999. They're essentially the same. That means that, n is the same as n minus 1. So we can have n squared divided by 2, and then we bring in the V for concentration. Made a little correction there. Well, that is going to turn into our correction factor. A is the constant. That's our unit of concentration, but we're going to be squaring the whole thing.